Okay, so to try and understand this, let's think about a couple of simple example flows. And the simplest flow we can think of is what's called a rectilinear shear flow. And there's a nice demonstration of this in the movie by John Lumley, who creates this beautiful experiment that we'll play here, where they're going to label a series of material points using essentially carbon powder suspended in a very viscous bath of glycerin. And there's two plates that are moving. The top plate is moving from the top left to the bottom right, and vice versa. And you can see these two plates are generating a shear flow, and we can see that these material elements are slowly being deformed. And so we have line elements that are being rotated and stretched, just like we've just thought about. And we should be able to represent that in terms of this velocity gradient tensor grad V. So here's what the flow looks like, and we're going to try and interpret this geometrically. So we have at the top, we have a definition of the shear rate, which is given in terms of the velocity gradient for our material element. And we can think about that as constant, and so it's written by u divided by h. And here would be our velocity field. So if we now evaluate the velocity gradient tensor that we've just derived, we'd write it out and it looks like this, and we can see that it's definitely not a symmetric tensor. There's only one term that's non-zero, which is the derivative of Vx with respect to y. And we should be able to write the velocity of any neighboring point in terms of the velocity at one point plus this gradient. And we've written that this gradient can be expressed in terms of a symmetric tensor and an anti-symmetric tensor that we've written right here. So what we need to do is we need to evaluate this symmetric and this anti-symmetric tensor. And we're thinking about the velocity. If we know the velocity at a point here, we should be able to think about the velocity at a neighboring point, a step size dy in either the plus or the minus direction. So if we carry this on, we can decompose this deformation into three components. We can think about it as a translation, which would be just the unit square moving at a constant velocity, combined with this idea of a deformation and a rotation. And shear is an equal contribution of straining deformation and rotation. So we might well write our pure deformation tensor, our symmetric tensor, as we've written it here, has got a symmetric term on either diagonal here. We can also express it in terms of a different coordinate system, however. We can think about not expressing it in x and y, but relating it to, say, a coordinate system x primed and y primed by rotating it through 45 degrees using a rotation matrix. And so if we take our rotation matrix, which will look like this for the cosines and sines of 45 degrees, then when we rotate this in this new frame, we can actually see that indeed it looks like a stretching in the x primed frame and a compression in the y primed frame. And so these are two equal ways of describing this deformation. One of them is in terms of shearing components, if you were writing it in xy, or you might think about it in terms of stretching in x primed and y primed. However, we also have to recognize that if we're thinking about it in xy plane, that it's a translation plus a straining deformation plus a rotation. And so we can also write the rotation as an anti-symmetric tensor, which we're given right here. And these would be the components of our of a vector, and the only non-zero term of the vector that we would write is would be given by omega right here, would be in terms of this. And so we can think about there being a rigid body rotation which is given by this kind of motion that looks like this. And we're going to see later on that what we call vorticity is nothing but twice this angular velocity. And the factor of 2 just comes from this idea of adding a tensor and its symmetric part transposed. So this would be the way we'll think about it in terms of a material element in a Lagrangian sense, but it's worth just remembering that we can also describe things in a Lagrangian sense as well. And so if we want to describe things not in an Eulerian frame but in a Lagrangian frame, then we recognize that these material elements are actually being deformed and being stretched. And so what is initially a square will eventually be deformed and will look like a rhombus, as we've shown right here. And so we can think about what happens to the change in the length. And in particular, some of you have been thinking when we calculated our shear component, you might be recognizing that this length, PQ, is getting longer in time. And in fact, it's getting longer in time at a rate that's looking like gamma dot, the shear rate, times the time elapsed, like this. Our average rotation rate of our two material axes is a combination of the two angles d alpha by dt and d beta by dt. In the case that we've got here, actually one angle is not rotating at all and only the other angle is. And so our average angular velocity is an average of 0 and this change here. And so in this case, d alpha is 0, d beta is not 0. And so indeed our average angular velocity is 1/2 of 0 plus this quantity. So that's where we get a 1/2 out of this. If we let time play forward, as you saw in the movie, material elements will get further and further and further apart. And so we can actually see that, in fact, that this angle will change in time. And we've made the approximation that the angle is small. But in fact, if we let the movie play for longer, then no longer will this be small. And in fact, the material element will indeed continue to rotate. And we have a differential equation for the change in the angle. And we'll actually find that indeed the angle begins to increase. And eventually, of course, the angle between the line elements will increase. We can no longer make our small angle approximation. And so the angle between the line elements will eventually increase in time and will look like this inverse tangent function. However, we're always going to just think about the instantaneous rate of strain, and if we're only interested in the rate of strain, then the rate of strain is connected to the angular velocity, as shown here.